So, Mohammad Zahir, absent. Mohammad Sattar,
Sir, some students have the problem with internet.
the problem with the internet.
No, no, they cannot enter the room. I mean, they cannot join the group.
If there is if they are in the waiting room, I accept them. But there is nobody in the waiting room at the moment.
I don't know, but they said that we cannot join the group. I don't know what this.
I don't know also. So, Mohammad Sattar, Asu, Juar, Juar, Mohammad Abdul Razzaq, Mohammad Suleiman. Mohammad Suleiman, are you there? Shaheen, Shaheen, are you there? Walid, Walid, very good. How are you, Walid? Alhamdulillah. Nahla. Oh, Shaheen, are you're there? Please answer me. Nahla, are you're there? Salam alaikum. Very good. Shoresh, are you there? Shoresh, Shoresh, Shoresh. Kaiwan just joined us. I saw him. Hussein, Hussein. We don't have a Hussein here.
It's Hassan.
Aha, Hassan Saleh. It is Mr. Hassan.
Yes.
Uh, Saleh is supposed to be with. Oh God. Bawai.
Yes.
Salam alaikum, Bawai.
Um,
Uh, wait. Dilan.
Yes, sir.
Salam alaikum. Dilan. Ardavan. 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 Sarbaz Sharif. Jihan. Jerjis. Salam alaikum. Salam alaikum. Ayeshe Rasul. I saw Ayeshe. Avan. Where are you, Avan? How are you, Avan? Avan.
She is here.
She's here?
Avan's mic does not work.
Oh, really? That's a shame. So, let me see. Yeah. Avan, presents for you. Don't worry. Now I'm changing it. Azad. Azad. Salam alaikum, Azad. Aras. Aras Fateh. Aras. Ali Muhammad. Mr. Ali. Where are you,
Yes,
Mr.
teacher.
Ali? Salam alaikum.
Alaikum assalam,
Muhammad
teacher.
Ali.
Yes, teacher.
Salam alaikum, Mr. Muhammad.
Alaikum assalam.
Nihad. Nihad Hamad Amin. Nihad absent. Somaye Hussein or Hassan. Somaye Hussein absent. Gile, I'm seeing Gile. Havan.
Yes.
Havan is also with us. Mustafa Sarhang. Mustafa Sarhang. Binai is here. Muhammad Rostam, are you here? Muhammad Rostam isn't here. Hemen Abdul Khaliq. Hemen, I see Hemen. Yunus, I saw Yunus. Khavan, I saw Khavan. Emad, Emad Tariq Muhammad Ali, not here. Ari, Ariz Vasman, I saw him.
Yes,
Ar-
yes, teacher.
Arzu, I'm seeing her. Farhad, are you here or no? I don't.
Yes, sir.
Oh, how are you, Mr. Farhad?
چطوری سلام؟
Salam. Jihad. Where is Jihad? Jihad absent. Good. Thank you, guys. Let us continue. Let us start our lecture. Now, guys, today, fortunately, we are going to be able to finish Note 5. And as I told you, at the end of the Note 5, there's going to be a homework waiting for you. You have to solve the homework and send it to me till next week. And after
Sorry,
you,
didn't read my name.
oh, Miss Lana, Lana, your name is not here on the list. I don't know why. I'm gonna write your name here. I'm gonna put in presents for you.
Sir, you mean we can send it after it, the homework?
It is 2 days from now, right?
Yeah.
You're gonna send it to me next Thursday, okay?
Okay.
Thank you very much. Now, so if you have, please look at the screen. We're gonna work on Note 5 today, okay? Now, in the previous week, we solved the 1D wave equation type 1. In this week, we're going to solve 1D wave equation type 2. The process is very much similar to the process that we went through for the other 1D wave equation that we saw. The PDE itself is the PDE for all the wave equations. No difference here at all. The boundary conditions here are different. We have Neumann boundary conditions, right? And our initial conditions are going to be first, initial position, and second, initial what? Initial velocity. Yes? Now, the solution using this method of separation of variables is just like what we saw previously. Now, we suppose u to be the multiplication of a function depending only on x and another function depending only on t. After replacing fg with u into the original PDE, we're going to have if G double dot equal to alpha 2 F double prime G. Okay? And then if we divide both sides by alpha 2 Fg, we're going to get G double prime over alpha 2G equal to F double prime over F. And we suppose that to be equal to minus lambda. That is our separation constant. Now, at the beginning of the second step, the thing that we do is to translate our boundary conditions to conditions in terms of f. Round over round x of u at 0 is equal to 0. That means f prime at 0 is equal to 0. And round over round x of u at L is equal to 0. That means f prime at L is equal to 0. Right? Now, just like the previous cases, we're going to have three possibilities for lambda. Lambda being negative, lambda being positive, and lambda being 0. We start with the first assumption that we can make. If lambda is negative, what's going to happen? By the experience that we have gathered up to this point, we know that we can't have a negative lambda, but we have to prove that. And that gives us this conclusion. F of x is equal to C1 hyperbolic cosine of square root of minus lambda x plus C2 hyperbolic sine of square root of minus lambda x. Now, because the boundary conditions that are translated in terms of f follow the cursor, look at the screen. Because we have the values of f prime given at 0 and L, first for this f that we have found, we find f prime. Right? Because we want to use the boundary conditions for f. Now, for cosine hyperbolic, the derivative is going to be hyperbolic sine, and for hyperbolic sine, the derivative is going to be hyperbolic cosine. Now, the first condition tells us that f prime at 0 is equal to 0. And from that, by putting 0 into f prime, we can conclude that C1 square root of minus lambda hyperbolic sine at 0 plus C2 square root of minus lambda hyperbolic cosine at 0 is equal to 0. And that means because hyperbolic sine at 0 is equal to 0 and hyperbolic cosine at 0 is equal to 1, we can conclude that C2 square root of minus lambda is equal to 0, and that means that C2 is equal to 0. Right? Now, because we know that f prime at L is equal to 0 and C2 is equal to 0, so f prime of x is equal to C1 square root of minus lambda sine or hyperbolic sine of square root of minus lambda x. If we put in L instead of x in that, we're going to have C1 square root of minus lambda hyperbolic sine of square root of minus lambda L equal to 0. Now, what is the conclusion that we can make here? We can conclude that square root of minus lambda is not 0. Hyperbolic sine of square root of minus lambda L is also not equal to 0, because L is unequal to 0 and lambda is also negative. Right? So the only option that we have is for C1 to be equal to 0. Now, C2 was equal to 0. Wait. C2 was equal to 0. C1 is equal to 0. That means F is equal to 0 or U is equal to 0. Huh? And that is the solution that we consider the trivial solution. Okay? We are looking for solutions other than U equal to 0. Okay? So, considering negative lambda is not going to give us any valuable solution. Now, the important point here is that for wave equations, guys, please listen to me. Guys, for wave equations, for the case that lambda is negative, we can't use the solution for G to conclude that lambda can't be negative. Okay? We have to solve the ODE for X and get two hyperbolic terms and try to show that their coefficients has to be equal to 0. The reason that we can't use the solution for the time ODE to show that lambda can't be negative was explained in the previous lecture, and you have to be very careful about that. Now, Binay, go ahead.
Here I have the problem when sine hyperbolic of minus lambda L is not equal to 0. What if the L is pi? So why can
It won't be equal to 0.
I don't know. Can you prove it or show?
Yes, yes. Very easily. That is a good question, anyway. Let me show it to you here.
Teacher,
What?
but I think only a sine hyperbolic or 0 is 0.
Exactly, that is the reason. Now, Muhammad Abdul Razzaq has given you the answer, Binai. I'm saying that, let me share this screen with you. Now, what am I saying here? I'm saying that if hyperbolic sine of something is equal to 0, then x is equal to 0. If hyperbolic sine of x is equal to 0, that means that x is equal to 0. Why? We can show it in two ways. First, using the graph of hyperbolic sine of x. The second reason can be this. This is a very ugly type of reasoning, but we can write hyperbolic sine is equal to what, Binay?
EX.
Yes. Very good. Exactly. It is equal to e to the x plus e to the minus x over 2, right? Now, if e to the x plus e to the minus x is equal to 0, it means what? It means e to the x plus e to the minus x is equal to 0, right?
Minus.
Oh, sorry, yes. Yes. Yes? Now, what does this mean? This means that e to the x is equal to e to the minus x. What does this mean? It means that e to the 2x is equal to 0. Sorry, is equal to 1. Sorry, e to the 2x is equal to 1. And that means what? Do you agree with this part, Binai?
Kind of.
Why kind of? You should completely agree with it. Why? Because e to the minus x is equal to what? It is equal to 1 over e to the x, right? And now, when we have e to the x is equal to
I got it.
آفرین. When we have this, we can say e to the x times e to the x is equal to 1. And that means e to the 2x is equal to 1, right?
Yes.
Now, what does that mean? That means 2x is equal to what? That means 2x.
Yeah.
Exactly. Who said that? Thank you, Walid. Your voice
Mr.
has
Einstein
changed.
Walid.
Huh?
Mr. Einstein Walid.
Mr. what, Walid? Einstein?
Einstein Walid.
Ah, yes. Our Einstein Walid. Thank you, Mr. Walid. So, 2x is equal to ln of 1. Now, ln of 1 is equal to what? Binayan. ln of 1, 0, yes. And that means that x is equal to 0. Yes?
Yes.
But the better way to show this is using the graph of the hyperbolic sine of x. Now, let me show you the graph. So I'm sharing. Now, do you see my browser, Binai? And everybody, do you see the browser?
Yes.
So this is the graph of hyperbolic sine. You see that the value of the hyperbolic sine is 0, right? Only when x is equal to 0 and nowhere else, right? Thank you guys very much. Guys, there's 1 minute left of this meeting. I'm gonna finish the meeting and I'm gonna send you another link. Be back in now. We were working on 1D wave equation type 2. Let me find the tab. Now, at the end of the previous meeting, Binoy asked why why do we say that if sine hyperbolic sine of something is equal to 0, then that means that the thing is equal to 0, right? So we said that if hyperbolic sine of x is equal to 0, then x is equal to 0. And what does that mean? It means that if x is not equal to 0, then hyperbolic sine of that x is also not equal to 0, right? Now, so here we concluded that C1 has to be equal to 0, and that means that f has to be equal to 0 and u has to be equal to 0. Right? Now, so we showed that lambda can't be negative. So let us continue and see what happens if lambda is equal to 0. Now, before we go through with that, let me ask you a question. Are we going to have a solution other than 0 when lambda is equal to 0 or not? Can you tell me without going through the solution by the previous experience that we have?
Yes, I
Yes.
guess.
Yes. And how did you guess, Binai?
The boundary condition is u of x.
Yes, we have Neumann boundary conditions, and Neumann boundary conditions are going to give us a solution for lambda equal to 0. We saw that when we were working on 1D heat equations type 2, right? Very good. So you see that the structure of the solution that you're going to get depends a lot on the type of boundary condition that you have. Yes? Now, let us go through the solution. If lambda is equal to 0, it means that f double prime is equal to 0, right? And that means f of x is equal to ax plus b, right? Knowing that f prime at 0 is equal to 0, and seeing that f prime of x is equal to a, we can say that a has to be equal to 0. Then, knowing that f prime at L also has to be equal to 0, since f prime is equal to a, which is a constant, these boundary conditions that are given at 0 and L don't make much difference to us because f prime is constant anyways. So the second boundary condition also gives us the same conclusion for A. Doesn't give us a new conclusion. So using the two boundary conditions that we had, we can only say that A is equal to 0. And what is the meaning of that? The meaning of that is that f of x, which is equal to ax plus b, is equal to a constant which is denoted here by b, right? And this constant can be a non-zero constant, right? So we have found a solution for f here, as Binai said, right? Now, when f is equal to that, we have to also find g. So we have a solution for u. Now, here, g double prime is equal to 0 also. Sorry, g double dot is equal to 0 also. And that means g of t is equal to ct plus d, right? Now, look, what is the conclusion that we can make at this point? At this point, when gt is equal to ct plus d, unless c is equal to 0, please pay careful attention to the screen. Please, all of you, look at the screen. Now, we don't have boundary conditions for g, right? But here we can say this. We can say that unless c is equal to 0, then gt goes to infinity as t approaches infinity, right? And what would be the problem with that? If gt goes to infinity, it means that u goes to infinity, right? What does that mean if u, which was the displacement of our string from the initial position, if that displacement is equal to infinity, it means that our string is torn apart, right? That is the meaning of having u go to infinity. Yes? So, we have to have c equal to 0. And what is the implication of that? The implication of that is that gt is equal to a constant, and that constant can be a non-zero constant, right? So, what did we do here? We found a solution for f. We found a solution for g. So, we have found a solution for u, which is the multiplication of them. So here we can say that for lambda equal to 0, u can be equal to a constant. So this is one of the solutions that we have, right?
Excuse me.
Go ahead, Lana.
In the base that you determine that f is equal to constant, you said c equal to 0 for g of t. On this
Yes.
base, because the boundary condition is just for f, I think.
Yes,
And then
exactly.
on the base of f, you said c equal to 0
No,
for g of
no. I didn't say g of t is equal to 0. I said,
you said
uh-huh,
c equal to 0,
uh-huh.
so that g of t is equal to constant, right?
Yes, exactly. And Lana, why c has to be equal to 0?
My question is here, sir.
Uh,
I mean, on what basis?
exactly. Look, Lana. So what I'm saying that if c is not equal to 0, then the limit of gt when t goes to infinity is equal to infinity.
We don't want this solution, right?
Exactly, we don't want that. Why? Because if g goes to infinity, then u goes to infinity. Right? What is the problem if your u goes to infinity? Why we can't have u to go to infinity? Because the physical meaning of u is the displacement of the string from the equilibrium position. Huh? If that displacement is equal to infinity, it means that the string is torn apart. Yes? Thank you for your question. Now, so if lambda is equal to 0, then u can be equal to a constant, right? Now, what if lambda is positive? This is the main part of our solution. The solution for positive lambda. Now, if lambda is positive, we can say f double prime plus lambda f is equal to 0, and we can readily conclude that f of x is equal to C1 a cosine function plus C2 a sine function. Because we have if the values of f prime at 0 and L, we calculate the f prime of x, which is equal to minus C1 square root of lambda sine of square root of lambda x plus C2 square root of lambda cosine of square root of lambda x. Yes? Now, knowing that f prime at 0 is equal to 0, we can conclude that C2 has to be equal to 0. Then, knowing that f prime at L has to be equal to 0, we can conclude that minus C1 square root of lambda sine of square root of lambda L has to be equal to 0. And as we know, this gives us, this equality that I'm pointing to, gives us two options. The first one is to have C1 is equal to 0, which gives us u equal to 0, unwanted solution. Or we can have sine of square root of lambda L to be equal to 0, right? And what is the meaning of that? The meaning of that one is that square root of lambda L is equal to, guys, please pay attention to the screen. That means square root of lambda L is equal to n pi, where n is equal to any positive integer, 1, 2, 3, 4, till positive infinity, right? The conclusion from that is lambda is equal to n pi over L to the 2. Or we rename n pi over L to lambda n, and we say lambda has to be equal to lambda n to the 2. Yes? Just like the previous case for the 1D wave equation. Now, if we replace this lambda into the function f, what are we going to get? We're going to get f of x equal to c1 cosine of lambda n x. Yes? And that is exactly what we expected. When we have Neumann boundary conditions, we know that the eigenfunctions are going to be cosine functions. This part is extremely important. You should know that. When we have Dirichlet boundary conditions, guys, please look at me. Listen to me. When we have Dirichlet boundary conditions, our eigenfunctions are sine functions. And we don't have a solution for lambda equal to 0. When we have Neumann boundary conditions, our solutions are cosine functions, and we have a solution for lambda equal to 0. When we have mixed boundary condition type or type 3 boundary condition, we're going to have an eigenfunction in the form of sine, but the eigenvalues are going to be in the form of n minus 1 over 2 pi over L. For type 4, the eigenfunctions are going to be cosine of eigenfunctions forementioned, right? And for boundary conditions type 5, we have sine solutions and cosine solutions together. And we also have a solution for lambda equal to 0. That is what happens for both heat equations and wave equations. Yes? Now, I'm going to continue sharing the screen with you. So f of x is determined. Now what is our duty? Our duty now is to find gt. Yeah? So g double dot over alpha 2g is equal to minus lambda n to the 2. Or g double dot plus lambda n to the 2 alpha to the 2 g is equal to 0. That means gt is equal to c k1. K1 Forest. K1. Here we have K1. K1 cosine of lambda n alpha t plus K2 sine of lambda n alpha t. Right? For all the values of n from 1 to infinity. So you see that now G is determined. Now, with f being determined and g being determined, we have u. U of x and t equal to f of x gt is equal to a constant cosine of lambda n alpha t cosine of lambda n x plus another constant sine of lambda n alpha t cosine of lambda n x. Right? You should be very careful when it comes to the writing of u of x and t. So, we have an infinite number of solutions found for lambda positive, and also we have a solution for lambda equal to 0. But lambda can be any number. So all of these solutions are valid simultaneously. And according to the superposition theorem, the solution for u is u of x and t equal to alpha 0 plus sigma n from 1 to infinity cosine of lambda n alpha t cosine of lambda n x plus bn sine of lambda n alpha t cosine of lambda n x. Yes, this is the solution that we get at the end of step 2. What was the solution that we got at the end of step 2 for 1D wave equation type 1? It was sigma n from 1 to infinity an cosine of lambda n alpha t sine of lambda n x plus bn sine of lambda n alpha t sine of lambda n x. Do you remember? You should. So guys, what should we do at this point? We have to go through a step 3 and satisfy our initial conditions. Now here we have two initial conditions: initial position and initial velocity. Do you remember? Now we have to use those two initial conditions to find what? Look at the screen. To find an, to find a0, to find an, and to find bn. Right? So first let us try to find a0. Finding a0. First we know that u of x and 0 is equal to f of x. And by using the solution that we found at the end of step 2, we know that u of x and 0 is equal to this one. So a0 plus sigma n from 1 to infinity an cosine of lambda nx is equal to f of x. Now for finding a0, if we just do an integration from 0 to L, we can easily find a0 to be equal to 1 over L sigma, integral from 0 to L f of x dx. Right? If we want to find an, we have to multiply both sides by a cosine term and then do the integration. And we can easily conclude that an is equal to 2 over L integration from 0 to L of f of x cosine of lambda n x dx. Right? Now, when we want to find Bn, what do we have to do? We have to use the initial velocity. And in order to be able to use the initial velocity, which is our second initial condition, we have to calculate rho u over rho t. Look at the screen. We have to calculate rho u over rho t. Now, if u of x and t is equal to this, then rho over rho t of that u is going to be equal to this. Right? This cosine of lambda n alpha t is going to turn into minus lambda n alpha sine of lambda n alpha t. And this sine of lambda n alpha t is going to turn into it's going to turn into lambda n alpha cosine of lambda n alpha t, right? That is the only change that we're going to see. Excuse me, guys. So, دارم میارن؟ آها این چیزه، این که این چی داشت میگفت؟ قراره بیاره؟ بعد چیزه این آینه رو گفتش که کی گفته؟ آها. Excuse me, guys. Excuse me. So, now, rho over rho t of u of x and 0 is equal to what? We have to replace t in this with 0, right? Now, what's going to happen if we do that? Sine of 0 is going to turn into 0, and this whole term is going to disappear. And cosine of 0 is equal to what? It's equal to 1. So after the replacement, we're going to have sigma n from 1 to infinity bn lambda n alpha cosine of lambda n x. And the initial velocity that is given to us is g of x. Now, from this one, we can easily find bn. How? By multiplying both sides by cosine of lambda mx and then integrating from 0 to L. And that is going to give you what? That is going to give you Bn equal to 2 over L times lambda n alpha integration from 0 to L of g of x cosine of lambda n x dx. Yes? Now what? Now our solution is complete. We have found u of x and t. We have found a0 and an and bn. This is the summary of our solution at the beginning of page 10. U of x and t is equal to this. A0 is equal to this. Also, you have an and bn. Guys, questions? Go ahead. Go ahead. Thank you very much.
Why we say f and g is zero constant? I think sometimes a0 can be 0.
Why do we say f and g what? Can you repeat your question?
Zero constant.
Can you repeat your question, Walid?
Why we say f and g is non-zero constant when lambda equal to 0?
Aha, you were talking about lambda equal to 0. Why? Because if they are equal to 0, then the meaning is that u is equal to 0. What are we saying here? Look at the screen valid. What are we saying here? We are saying that there is the possibility for f to be equal to a non-zero constant. Huh? We are not saying that it is necessarily equal to a non-zero constant. If f was equal to 0 or g was equal to 0, then what would we have? We would have u equal to 0, which is the solution that we are trying to avoid, right? So the meaning of this equality equal to a non-zero constant, that is that there is a possibility for f to be equal to a non-zero constant. Also, that is true for g. Did you understand what I mean, Vali?
So A0 can be 0.
A0?
Yes.
A0, yes, can be 0. That is a different question. You're talking about... A0, yes, can be equal to 0. Yeah, for sure. Because it is equal to the result of an integration. If the function f is a kind of function that the net area under its curve in one period is equal to 0, then a is equal to 0. Yeah, for sure. But there's also a possibility for a0 to be equal to a non-zero constant. Yeah? Did you completely understand? It was a very good question. Very, very good question. Impressive question, actually. Thank you very much. Thank you very, very much. Now, guys, what do we have here at the end of page 10? We have your homework that we talked about. Yes? You have to solve this homework and give it to me next Thursday. Okay? Thank you. Now, guys, let us go to note 6. So note 5 is over. We're going to start note 6. What?
Sir, let's finish it here.
Oh, guys, just take a look at note 6. I'm going to share it with you. 1 minute, 1 minute. 1 small minute. Look at note 6, guys. The title of the note is non-homogeneity. Okay? But the first two examples in this note are just simple examples of 1D wave equation. Okay? And let us solve example 12 and example 13, and it is going to take 10 minutes. And then we can go home. Okay? Actually, we are at home. We can... I don't know. Huh? Who is talking? So, guys, okay, so we're gonna have one more meeting, one more Zoom meeting. Okay? Let us finish this one, have a bit of rest, and come back and solve example 12 and example 13. And then we can lie down in our beds. Okay?
Teacher,
Go ahead, Ayesha.
we have work at home.
Ayesha Gyan, we have,
Working with mom.
it is Eid,
Tuesday
yes.
they will
I
be
have
off.
also a lot of work at home also. So that is not a good reason. Your most important work is studying. You are students. This is your work.
Studied a lot, teacher. We are tired.
Tell to our mom, not us.
What, Binai?
Tell to our mom, not us. I understand you, but my mom not.
You have to make your moms understand. It is only, guys, according to it is a 3-hour class, so I have the authority to make you stay at the class for 2 more meetings. But I'm only going to do that for 1 meeting. So thank me. Thank me. So guys,
Sir, the
uh,
example you have explained it, sorry,
oh,
with my ultimate respect, but the example you have explained it in one session, you would have taken 3 hours to complete it in the class.
no.
You know?
Oh no, Binai.
Then you have to take 2 classes for explaining 1D heat equation type 1.
Because what was the reason? Because at that stage you didn't know anything about the procedure, right?
Right.
And I had to explain it word by word,
And
letter by letter. Huh?
Right, everything, but right now
Yes, yes. But now I'm not taking 3-hour classes. We are taking 1-hour classes. If we spent all the 3 hours, we would still be further down the road in our course. Do you agree, Binai?
Yeah, you're right.
Yeah. And it took that much time in the beginning because you didn't know anything about this process of solution for, you didn't know anything about the separation method. So I had to spend more time when you were new to the subject. But we don't need to.
Let's make a deal. You are free to extend the classes and extend the examination time. Quite fair, right?
Yeah. I'm gonna be very kind to you in the examination. Don't worry. Don't worry. So, guys, let us have a 10 minutes rest, 15 minutes rest, uh, 15 minutes rest, and then have another meeting, and then we can go back to eat stuff. Okay? Thank you very much. Thanks for now.
Bye.
Bye for 15 minutes. Now, example 12 at the beginning of note 6 is an example on 1D wave equations. Now, let us start reading the example. It says, consider a vibrating string of length L equal to 1. Okay? So the value of L is given to you. That satisfies the wave equation ρ 2u over ρ t2 equal to ρ 2u over ρ x2. Right? Now, what is the conclusion that you can make here? The conclusion that you can make is that alpha is equal to what? Exactly. Alpha is equal to 1. Now, please pay very close attention to the screen. Look. It says, assume that the ends of the string are fixed. what is the meaning of this? Assume that the ends of this string are fixed. Can anybody tell me?
So does it have relation with boundary condition?
Exactly. It has a relationship with the boundary condition. But Lana,
X, u at 0 and t and u at l and t equal to 0.
exactly. In other words, the meaning of this is that the value of u at both ends is equal to 0, or it means that we have Dirichlet boundary conditions, right? And we have a 1D wave equation type 1, right? Yes? That is a very important point to keep in mind. This interpretation is the key to the solution of this exercise. Now, there is even more information given to us here. Now, what do we need? We need initial conditions. But the example says the string is set in motion with no initial velocity. With no initial velocity. What is the meaning of that? It means that round over round t of u at x and 0 is equal to 0. Yes? Thank you very much. And the initial position is equal to this. U of x and 0 equal to sine of pi x. And we have to solve this PDE to find u of x and t. Right? Now, we are told that the ends of the string are fixed. Knowing L equal to 1, we can write the boundary conditions at u at 0 and t equal to u at 1 and t equal to 0. The initial conditions, as the example says, are u at 0 and t, u at x and 0 equal to sine of pi x, and u of t at x and 0 equal to 0, because the initial velocity, as the example says, is equal to 0. Now, the PDE with boundary and initial conditions is this system. This system that you have here. Right? So, let us get down to the solution. Now, the process of the solution is just like the previous examples that you've seen. In this example, we want to focus on some very important side point. Because of that, we have jumped to the final solution and we have ignored the process. But there are things that we need to discuss about the final solution. So, first, let us find the final solution. U of x and t, after going through all that process that you're familiar with, is going to be equal to what? This sigma. Look at this sigma. How do I write this sigma? There are two things that you need to know in order to be able to write this sigma. Please pay utmost attention here. Look at the screens and listen to me carefully. Look, this sigma has two things. One is f of x, which is equal to sine of n pi x. The other is g of t, which is equal to what? Which is equal to something times cosine of n pi t plus something times sine of n pi t. Right? Now, why f of x for this problem is equal to sine of n pi x? because we have a 1D wave equation type 1, and the solutions are going to be in the form of sine of m pi over L x, and L being equal to 1, sine of m pi over L x is going to become equal to sine of m pi x. Yes? Did you understand what I said? Did you understand what I said? I hope so.
Yes, sir.
Very good. Now, for g of t, what do we do? Knowing that eigenvalues are n pi over L to the 2, which is what? Which is n pi to the 2, the solution. And knowing that alpha is equal to 1, the solution to the time ODE is going to become something times cosine of lambda n, which is n pi alpha t, alpha equal to 1, so cosine of n pi t plus sine of n pi t, right? Binai, did you understand me?
Yes, sir.
Very good. Thank you very much. So u of x and t is equal to this. We have to find an, which is 2 over L integration from 0 to 1 of f of x sine of n pi x dx, which is 2 times integration from 0 to 1 of sine of pi x sine of n pi x dx. The result of this integration that you have here is equal to 0 unless n is equal to 1, right? Here I should have written n equal to 1 and n unequal to 1. So you have to correct this. Okay? This 2 should be turned into 1. Okay? Now, this is your result for an. For bn, because g of x is equal to 0, the result of the integration is going to be equal to 0. Because g of x is equal to 0. Our job is easier here. So, let us replace an and bn into u of x and t, which is equal to this, and see what happens. All the bn terms are equal to 0, so this whole part vanishes. And for an cosine of n pi t sine of n pi x, we know that an is equal to 0 unless n is equal to 1. And for n equal to 1, an is equal to 1. So u of x ante is equal to cosine of 1 pi t cosine of 1 pi x. Right? This is our final solution. U of x ante equal to cosine of pi t sine of pi x. So, guys, this solution that we have found for a wave equation, what is the meaning of this solution? The meaning of this solution is that the displacement of the string from its initial position is seen in the behavior of this function that you have here. Now, if you draw the graph for this two variable function u of x and t equal to cosine of pi t sine of pi x, you're going to get to the graph that you see here. Look at this graph in figure 1. This axis here is the x-axis. Look at the screen. And this axis here is the time axis. So this part is the middle of the string, and these two parts are the two ends of the string which are fixed at a specific point. You see that if you draw the graph for that solution, cosine of pi t sine of pi x, this is going to be the graph. Meaning at the beginning, the string is pulled up. When we let it go, then the string goes down, down, down. It becomes straight. Then it goes away in the opposite direction. Yes? Till it reaches a minimum, and then it comes back up again. Right? Do you feel this behavior of the string? If you have played guitar, you see that this is how a vibrating string behaves like. Now let us
Sir,
go ahead.
so where's n on this graph?
N?
Because this function is only valid when n is equal to 1.
No, absolutely not. Absolutely not. Look at the solution that we have found, Binoy. The solution that we have found is u of x and t equal to this, and an for various values of n is determined. It was either 0 for n equal to 1 or 1 for n equal to 1. Sorry, it was 0 when n was not equal to 1. This 2 should be changed into 1, okay? So an is equal to 0 when n is not equal to 1. Do you agree? What is the meaning of that? It means that all of these terms are going to be equal to 0 except for a1 cosine of pi t sine of pi x. Do you agree, Binay? Hello, do you have my audio? Binay, what happened to you?
Sir, I hear you.
So answer me. Look, what did I say? I said an is equal to 0 unless n is equal to 1. Huh?
Yes. Yes.
So the meaning of that is that an cosine of n pi t sine of n pi x is equal to what? All of the terms are equal to 0 except for a1 cosine of 1 pi t sine of 1 pi x.
I
Uh-huh.
get it. So sine 1 pi t equal to 0. So
Exactly. And a1 is equal to what? a1 is equal to 1, and all. Okay, let us continue with the previous example that we were working on. Now, have this graph in page 3 of note 6 in mind. This is the figure that you typically expect to be the figure of a wave, right? Now, let us consider some specific times. Okay? At time t equal to 0, u of x and t is equal to what? Look, if we put in 0 instead of t in equation 159, then u of x and 0 becomes, here instead of t I should write 0. U of x and 0 becomes sine of pi x, right? Now look at the graph of u of x and t and see whether or not we have that. We see at time t equal to 0, then what do we have? We have sine of pi x, right? It's a sinusoidal function here, right? What about time t equal to 0.5? If t is equal to that, then cosine of pi over 2 is equal to 0, and u of x and t becomes 0, right? Do you agree? So we see that at time, this axis is for time. It starts, look at the figure and follow the pointer. Time t equal to 0 is here, and as time goes by, we move in this direction. At time t equal to 0.5, meaning half seconds past the start of the vibration, u of x and t, as we calculated, is equal to 0, right? And that is what we see here. We see that u of x and t at t equal to 0.5 is equal to 0 for every x, right? And the figure is a plateau, right? Now, at time t equal to 1, what do we have? Instead of cosine of pi t, we have cosine of pi. Cosine of pi is equal to -1, so u of x and 1 is equal to minus sine of x pi, right? And you can see that clearly in this graph that you have here. At time t equal to 1, the graph looks like minus sine of pi x. Yes? Do you have a question here? This part is very important. And guys, how do we draw this graph for cosine of pi t sine of pi x? How do we draw this graph? And a more important question is, how do we solve equations like this, partial differential equations like this, using various softwares that exist out there? Now, I have solved these equations using MATLAB, and MATLAB has drawn this figure for you. This figure is drawn by a software which is called MATLAB. And the code that gives you the solution for various 1D wave equations is also included, is written by me as a MATLAB file, and I have given to you this file and it is uploaded in the LMS system, in the Moodle system. If you go there, you can find the code that generates the figure for example 12 and example 13. Okay? Now, one conclusion, go ahead. Yes? 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 The process of extracting a graph from a, sorry, the process of extracting a function from a graph is the subject of a many various mathematical methods, which one of the most famous of among them is a method called regression, right?